Hi, welcome to the Signal Pad. In this episode, we're going to have some fun with this Keysight LCR meter. This is an E4980A. It's a very high-end precision LCR meter by Keysight, and it has 0.05% accuracy over all the frequencies from 20 Hz to 2 MHz, 4-digit resolution, and a whole bunch of built-in functions. This one is a fully loaded instrument. Now underneath it is the Shahriar E4980A. I actually repaired this unit in one of the previous videos. This is a pure capacitance meter, very high speed, again very accurate, intended for manufacturing and binning and so on, so it can be quite useful, especially when connected with the back to some automated measurement setup of some kind. But this LCR meter is a whole other thing, and I want to talk a little bit about how it works internally, and why does it have 4 connectors and some very basic stuff. But the reason I wanted to play around with it is because about 20 years ago, when I first learned about how capacitors were made and what was the theory behind their operation, I built some capacitors myself and did some experiments, which was a lot of fun. But of course, I couldn't dream about having access to something like this. So now we're going to repeat some of those and see what happens. Now, in theory, in order to determine what the impedance of a device under test is, you simply have to measure the relationship between the voltage across the device and the current through the device. This is just Ohm's law. And it doesn't matter that the impedance has reactive components to it or imaginary components to it. The theory still stands, of course. And I'm sure you're familiar with the concept of impedance as well. We're talking about devices that do not simply have a resistive component to them, but also an imaginary part, a reactive part, capacitive or inductive, which then creates a complex impedance, represented often by a vector on this real and imaginary plane, then denoted by the value of Z. So all of that is pretty straightforward. Now, if you wanted to measure this, how would you measure it? Well, you could measure it in a very simple way. You could have an oscillator that applies some kind of an AC signal through a known resistive source, like this one. It doesn't have to be resistive, but it makes it easy, like a 100 ohm here in this case. And then you measure what is the voltage that develops across your ZX, your unknown impedance, and what's the current going through it. Once you know those two things, then back to Ohm's law, and of course you get what the impedance is. Now, the frequency of the oscillation here matters because these things are not just purely of one type. We'll talk about that in a second. No device really is only purely resistive or capacitive or inductive. There are always a mixture of all of them, and they have to do with the parasitic of the devices. I'll talk about that a little bit at the end. So why not just build an LCR meter like this? And what's the deal with having these 4 connectors to the front of the instrument? Well, if you have a very inexpensive LCR meter, like a handheld one, or a really cheap one, that's basically what they're doing. They're doing something really simple. But this is susceptible to a lot of errors. First of all, consider the length of this cable. This cable has its own inductance. This parasitic inductance of the cable combines with the ZX that you don't know. Well, you're going to ask, well, why not just null that? And of course, you can null it, and there is nulling performance that is built into these instruments in order to create and zero out an open or a short so you can figure out what all the setup parasitics are. But it's not so simple as that, because as you move the cable around, you're going to create a whole new environment. These cables couple to the environment in different ways. For example, they can capacitively couple to the environment around you. And this capacitance is going to mix with the device you're measuring, and as you move the cables around and things become close to it, you're going to have a different capacitance each time. And of course, you can also create a magnetic field because you're applying an AC signal through a conductor that's going to create a magnetic field. And that's going to couple to other lines into mutual inductance, and then that's going to add up to your measurements too. And every time you move the cables around, the 2 cables that can get close to each other, they're going to mutually couple to each other. And that's going to throw your measurement off too. Meaning that this would be very difficult to build something that has a repeatable measurement performance because of the variation in the setup every time you want to measure. So of course, that's not how they do it. They do it in a much more complicated and elegant way. And this is a rough block diagram of how these measurements are done. You can immediately recognize that the beginning of it, the part we just showed, in terms of having an oscillator and an output resistor, that is still needed. And that's exactly what you see on the left side. So HCUR is the high current part, and there's a high potential, and a low current and a low potential. And here's a device and the test in the middle. So let's see what happens when you do this. Well, the clever part of this is that each of these HCUR, HPOT, and so on, they are actually all coaxial. So every time you send a current through the center conductor of the coax towards your device under test, the outer shell, the outer conductor of the coax, carries the current in the reverse direction. They're not grounded. So that balances itself out and eliminates any magnetic field outside of the coax, so then for mutual inductance between the cables is immediately eliminated. So this is very, very useful. That means that you don't have to worry about how the cables are moving around or interacting with each other because they're not producing any external magnetic field. But that doesn't end there, because even though they're not producing any magnetic field because they have current in the opposite direction, they may still have a voltage on them. And that voltage then interacts with the environment by creating an electric field. And then that would capture any parasitic capacitance that could be sitting there. So that's why they use what's called an Autobalance bridge. It's a clever technique where you monitor the voltage at some node, use it in a feedback path with another oscillator that adjusts to the original oscillator frequency, and that locks together, creating a virtual ground right at the intersection of the low current and low potential port, allowing this node to become a virtual ground following any swing of voltage that's on the DUT, canceling it out at this point. And as soon as you cancel it, well, you can measure exactly how much current is induced, because you can figure out how much you need to apply to cancel it. And that's where you perform your critical measurement. So that's how you get the current and the voltage. So it's very clever. And there is some disadvantages with this Autobalance bridge, because it cannot run at very, very high frequencies. Now here we're dealing with 2 megahertz, so it's pretty straightforward. But LCR meters that Keysight has, for example, that operate all the way to 3 gigahertz, are going to have a much tougher time, and they have some techniques to take care of it at these much higher frequencies. So you can see, by creating a bidirectional current, mutual inductance is gone, and by creating a virtual ground, parasitic capacitance is gone. And that way you don't have to worry so much about the environment changing. So that also means that what you want to do is you want to keep these high current, high potential, low current cables separate from each other up until the very last minute before they touch together at the DUT. And that's exactly what's going on when you do a measurement. So when you do a measurement, you have these 4 ports. That's the front of the LCR meter that we just saw. And you have these coaxial cables that are all connected, and they all come down. And then right at the point where you want to hit the device of the test, they join together right at that point in order to measure this. And then everything else is taken care of through the calibration and what we just talked about. So yeah, it's pretty nice and elegant, and it's a very standard technique, of course, nowadays to measure any kind of LCR devices like this. So then we're going to take a look at this. But there's also a little bit more about why the frequency matters. Well, as I said, no component is a pure capacitor, inductor, or resistor. There's always a parasitic element associated with it. So for example, a capacitor can have leakage across it. That leakage is a resistive part, and that can be modeled using a parallel resistor. There's also a series resistor associated with it at the same time, and that's this series connection, and you've heard of ESR and so on. But then you also have to adjust your instrument depending on what you're measuring. So if your capacitance is really small, then the resistance in series with it is not very significant, but the resistance in parallel with it is now a lot more significant. So depending on what you're measuring, there are rules of thumb of how to set up the LCR meter to get the most accurate and also the most relevant information you want to extract from your reactive component, from whatever it is you're measuring. And it's also the reverse for the inductors, of course. Now it becomes even more complicated across frequency, because everything has its associated inductive and capacitive parasitics too. So this element in reality also has some capacitance in parallel to it, and it may even have capacitances to ground and so on. And these models become more and more complicated and have to include multiple devices, components at the same time if your frequency is very high. So if you measure, for example, let's say your inductor at 1 hertz, you're going to get some value of inductance. But if you measure it at 1 megahertz, the parasitic capacitances begin to kick in. And at some point, the parasitic capacitance and the actual inductance perfectly cancel each other out. You get this resonance point where the impedance essentially goes very high, only limited by the resistive elements of the inductor. That point, then the component switches from being inductive to capacitive. And you can see that sometimes when you measure it. A very important parameter in choosing what component you need to put in your devices in order to not resonate at the frequency you're interested in. This stuff, of course, also happens inside of integrated circuits. And when we design things in the millimeter wave frequencies or even in the near terahertz frequencies, we have to take all of this into account. And our models for these devices can have 20, 30 components in them, so they can be really complicated. So now that we have a rough idea of how all of these things connect together, let's go and do some fun experiments. Now, another fun thing about these LCRs are the different fixtures that you can buy for them. So I've been hunting on eBay for many years trying to get as many of the different variations and specialized modules as I can. They can be really expensive. These allow you to measure a particular form factor device in a very easy way. So these are obviously for very large passives, and they're in two different form factors here, one allowing you to measure devices that radial have pins on each side. You just squeeze them between these two leads to measure them, and the one on the left is more like devices that look like that. You just press it into this. But look at how clever and simple the design of these things are. So if I remove this from here, you can see on the inside two plates, one at the top and one at the bottom. And those two plates basically come in contact with the center pin of the HPOT and HCAR, the high potential high current ports of the LCR meter. So you can see they're not touching each other. Remember, we said that you don't want them to come in contact with each other up until the latest point possible before hitting the device under test. So even when you place this inside, there's two plates in here that are free to move, and they're not touching each other neither. So when you squeeze this in the middle, now those two plates have a little gap in the between them. They're not actually in contact. And as soon as you push something in the middle of it, then that pin is the only point where the center pin of these two begin to touch each other, right where that pin is entered between the two plates. And look how clever it is, and you can see the rest of it is open. So that's how it brings that connection as close as possible to the device under test, in this case, this capacitor here. So let's look at a setup here. We have a frequency of 20 Hertz, so very low frequency. The level of the signal being applied to the device is going to be 1 volt. Right now I haven't zeroed anything, so you're basically measuring some of the noise that's in the environment. It goes up to a gigaohm here. And this is in femtofarad, of course. It's just gibberish, and if I can bring my hands close to it, I might be able to influence it a little bit. So at the same time, you can see what kind of current is going through the device. It's measuring in a picoamp, and that's why it's jumping around. And the voltage measuring is 999 millivolt, which is very close to the level that's being applied from the device itself, because there's nothing in here, of course. Now you can change the level from 1 volt to up to 20. This one has the option to go very high voltages, and that's because some capacitors indeed change when you stress them, and there's a capacitance is a function of the applied voltage too. In this case, let's leave it at 1 volt. Let's plug in this capacitor. This is a 1000 microfarad 25 volt capacitor. We expect it to have a very good ESR, so I've already changed this to measure RS, which is a series resistor. Let's go ahead and plug it in. Of course, the orientation doesn't matter because this is an AC signal being applied. Let's see what we get. There you go, 986 microfarad, 225 milliohm. So it's a good healthy capacitor with a good ESR, and the value is very close to where it should be at 20 Hertz. Let's go ahead and now increase the frequency from 20 Hertz to, let's say, 100. You can see the capacitance already beginning to change. Let's go 1 kilohertz. Now it's really beginning to change. 10 kilohertz. Now it's lower. And as soon as I hit 100 kilohertz, of course, we are now past its self-resonance. We're measuring a negative value. And that negative value is now an inductor. So we're beyond the frequency for which this capacitor is even a capacitor at all. That's because all the inductances and the capacitors are interacting and eventually passing the resonance. Let me go ahead, lower in frequency, so we can see if we can catch exactly where it happens. There you go, you see now it's minus 1 milli, it's right at the resonance. Let's go, there you go, so right around, so somewhere between 30 kilohertz and 40 kilohertz, we're hitting its peak of its self-resonance frequency. Okay, makes sense. So let's go a little bit higher, let's go to 100 kilohertz, and let's remove this one. Now this is a 1000 microfarad capacitor, so of course it's going to have a self-resonance frequency which is very low. But if I put a different capacitor, this one has it's quite a different value, much lower. Let's plug that one in there. And what do we get here? We get a 476 nanofarad, which is what it should be. It should be 470 nanofarad. And 100 kilohertz, it has no problem. Now I can go higher. 1 megahertz, you can see it's beginning to be affected. 2 megahertz, and we're already at the resonance. So this is what I was talking about when I said that some components are going to shift from one type to another. So here's a very useful one. This particular one ends in a tweezer, and this one is actually rated all the way to 15 megahertz. So for a different model of this that can go to higher frequency, it can still be used. And this tweezer allows you to measure, surface mount components, of course. So we can measure something really basic with this. So here is a 4.7 microfarad tantalum. You can see it's being held by the tweezers and no problem in the measurement at all. And you can measure things of different sizes, of course, because there's a certain displacement between the two leads. You can buy a model which comes closer or further apart. I really like this one, especially when you don't know what it is that you're measuring at all, and you can switch between inductor and capacitor to find out what it is. Now check out this fixture. This one is a really interesting one because it allows you to measure tiny surface mount components with very high precision and repeatability. It's adjustable. You simply separate these two needles from each other, which are spring loaded, and you put the device that you want in the middle right there, and these two needles come in and they put pressure on both sides, and then from there you can measure precisely the performance of that component, and you can bin them and so on and on. This is very specialized if you're doing a lot of tiny surface mount work. So this is a fixture that I put together using some parts from eBay. It's basically two clips going into this module over here, and each of the two halves of these tweezers are connected to one of the two cables. So again, they come together directly at the DUT. Now if you look, what I'm measuring is actually a diode. So we have right now a PN junction here that's between these two, and we have to be careful when we measure an active device like this because you don't want to forward bias it by applying too much voltage across it in AC. So I've taken care of that by applying only 100 millivolts to the device. But at the same time, I also have a DC bias across the device too, of minus 200 millivolts. Now neither of these two values are large enough to turn on this device, but you can see we're measuring a capacitance of about 40 picofarad. Now look what happens when I change the voltage. So we're going to go from minus 200 millivolts towards 0. 0 is minus 100. You can see the capacitance already changed quite a bit. If I keep going down, eventually we're going to hit 0. Just enter 0 here. There you go, 22. Now I can go in the positive direction. So let's say 0.1 volt. You can see it dropped again, and again, and again. So this is of course a Varactor. It's a PN junction Varactor, and we went from near being forward biased to completely reverse bias. And it's one of the fundamental voltage controlled capacitors that you can build, and it's very common in a lot of oscillators. Now we talked a lot about this, but I wanted to show you what I built about 20 years ago when I was playing around with capacitors for the first time. So here's my capacitor. It's really basic. It's nothing more than two parallel plates and some air gap in between it. So our dilectric here is air. It's made of a PCB with copper on one side, like this one. I just cut it into this shape, and I put a layer of tape on top of the copper side to insulate it as much as possible, and the screws are of course plastic so that they don't touch each other. So this is 130 millimeters on one side, 30 millimeters on the other side, and the gap is roughly 3.5 millimeters. Now if you calculate that with the epsilon of air in this case and ignore all the other effects, you get a capacitance of about 10 picofarad. So let's measure it, see if it's 10 picofarad or not. Go connect this to here. I've already try to zero this as much as possible, but let's see what we get. Here we go. Let's make sure it's nice and flat. What do we have here? There you go, 12.9 picofarad. So it's not exactly 10. So why is that? Well, that's because we're making the most simplistic assumption about the nature of this capacitor. We are ignoring the fact that there is, plastic on the corners. We're ignoring the fact that there is tape on there, which has a different dielectric constant than air. But more importantly, we're assuming the electric field is fully confined between the two plates. And it's not, because there is some fringing around this capacitor too. And that fringing field not only increases the capacitance because that's outside of the area we calculated, but it also goes through the dielectric material of the PCB too, which itself is about 4 or 3.5 or so. So that also changes everything. That's why we get a little bit more capacitance. But what is fun is to put different kinds of materials between this. And if you can measure the capacitance, you can tell what the dielectric constant of the material is, and you can also make some other interesting conclusions. Okay, so I added a factor of 4 averaging as well. Now let's take a look at this little piece of wood. Now this is tiny in comparison to the total area of this capacitor. But in theory, if I put this between the two plates, because its dielectric constant is more than air, on average it's going to increase the capacitance by just a tiny amount, because the electric field going through this is going to be different than going through air. Let's try that. Now this only really is possible with a very accurate and sensitive LCR meter. This is of course one of those. So let's try that. Here we go. So we're sitting at 13 picofarad roughly. Push this in the middle. Look at that, 13.15, just simply by that tiny piece of wood. If I remove it, okay, it goes back to normal. It's really quite amazing that you can measure the effect of something like this. We can also try maybe a piece of paper like this one. Here we go. Add that to the middle of this one. It's going to be a much larger effect because it's much bigger, and therefore a wider area of the total capacitance is now covered with a dielectric material that is not air. So that's now at 15.5 picofarad. Okay, let's try something a little bit more familiar. Here's some glass. Now I made this piece of glass in 2 different configurations. You can have it flat like this, or you can fold it over. When it's flat, you have twice the area, but the dielectric is thinner. And when you put it on top of each other, you get twice the dielectric thickness and half the area. Let's compare the two and see which one is more dominant in this case. So we're going to try it flat first, in the middle. We get 14.7 picofarad, okay? So let's remove it. We're going to fold it over, try exactly the same thing. In the middle, look at that, 15.5 picofarad. So it's different. And it's different. It's interesting to note that it's more impactful in this capacitor because of its total dimension and everything to have a thicker dielectric with a higher dielectric constant than if you have it flat. But it's even more interesting to put something that's conductive. Now this is very different, of course, because a conductive material like this is a piece of aluminum. By definition, a conductor cannot have electric field through it. That's a perfect conductor. Now this is not perfect, so it's going to be some really, really weak electric field through it, but that doesn't really matter. Let's assume this is perfect. So what happens when you put this in the middle? Well, if there is no electric field through it, you only have electric field above it and below it. So you actually are going to create two capacitors. Let's see what happens. Push this in the middle, like so. Look at that. 73 picofarad, a significant increase in the total capacitance here. And that's not surprising because if you look, there's no air gap left where this piece of metal is inserted. So basically what you have is you have a capacitor at the top from the plate to the top of this plate with only the tape in the middle being the dielectric, and then another capacitor at the bottom is identical to the other side. There's a bit of stray on each side as well. Those two capacitors are actually in series, so the total value of them are small. The total value is smaller than each of them. But because the dielectric is so thin now, the capacitance is so much higher, and we've reduced the total amount of gap so much that now the total capacitance is significantly higher than it used to be. Now, of course, you can combine things. If I push this all the way to the left side here, like so, we are at 72 picofarad, then I can still insert this, and its influence would be, quite a bit smaller. Just a little bit extra, like it used to have before. Yeah, so I had a lot of fun playing with this many, many years ago, and now we're measuring it with such a wonderful LCR meter. I thought you would enjoy it too. There you have it. I hope you enjoyed this. This was actually in part from a request of one of my Patreon supporters that I wanted to make a video like this. So if you haven't checked the Patreon page, please do so, and I would love to do more Patreon supported requests like this one. Now at the very top here is a 4338B. This is a milliohm meter. I've repaired this in a different video, and I'm really looking for the 4339B, and that's a high resistance measurement one. That's the kind of the twin of this one. I'm really looking to get one. I haven't been able to find one. If you know where I can grab one of them, please let me know, and then we can make a dual video for comparing the milliohm meter and the high resistance meter and see how they differ and how they work as well. As always, I'll see you in the comment section.